Hello, 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 and welcome again to calculus. So we've been going over, what did we do? We did high order derivatives, we did logarithmic differentiation, and now we're just going to move on with some applications of derivatives. You pretty much know what you're going to know about derivatives, which is awesome. And now we're just going to learn how they apply to the world and maybe a few more ways to help solve them if they get tricky. So, what does f prime of x tell you about f of x? This is a very basic question. What does it mean? It means the rate of change of f of x. In a simpler way, you could say it tells you the slope of f of x. So if something tells you the slope, let's say a function looks like this. Well, from here to here, the slope is going to be positive, right? And from here to here, the slope's going to be negative. So what does that mean about the point where these two places meet? Well, if something goes from positive to negative, like say this is the x-axis, if you go from positive to negative, at some point you have to cross 0. So that probably means the slope is going to be 0 here, right? Exactly. So let's determine, for instance, all the points where this function is not changing. What does not changing mean in mathematical calculus terms? Well, it means a point where the slope is 0. And how do we find where the slope is 0? Well, we know we're talking about slope, so right off the bat we know we're going to take the derivative. So derivative of that is 0. This is negative 6. And what is 10 cosine of 2x? Well, let's see. Derivative of cosine of 2x is negative sine of 2x times 2. So negative sine of 2x, so we know this is going to be a negative times a negative. That'll be positive. And then there is a times 2, so that's going to become 20 sine of 2x. All right, so if we want to know where the function is not changing, that's a place where the slope is 0. So how in the world do we find where the slope is 0 given this equation? Well, the derivative is the slope. That right there, that has a prime. That means that is a derivative. And by default, that is a slope. So we're trying to find where the slope is 0. So we set that equal to 0. And we get this. All right, so let's bring the 6 over here. Equals 20 sine of 2x. And now let's divide through by 20. We get 6 over 20, that's 3 over 10. So 3 over 10 equals sine of 2x. So yeah, if we have that, that means that it equals 0.3. And if you don't get this, just go back and review how to solve a trig function. When you have 2x equals 0.3, you say the answer is this, 0.3 plus 2 pi n. Right? Okay, so what we just did there was we found the points where the slope was 0. And we know that they will occur at 0.3 plus any time you have a repetition of 2 pi. Anytime you go around the circle, 2 pi. So let's say 0.3 was there on the circle. That means it'll occur there, it'll occur there, it'll occur there. See what I'm doing here? I'm just going around an infinite number of 2 pi times. Okay, let's see here. Determine where, oh Lord, y equals 4/5 x to the 5th plus 7/2 x to the 4th minus 10 x cubed plus 50 is increasing or decreasing. What does that mean? Well, let's see. We know what increasing and decreasing mean. Increasing is like that, decreasing is like that. How do we find where they're increasing or decreasing? Well, let's see. First, I'm going to write this function out here so that we have it clear. Then we're going to form our plan of attack, and then we're going to undertake it. This is our function. The derivative tells us what? The slope. If we know, remember how we said on this first page, if we know that a function's increasing here, that's where the slope, this, is positive, and then we know it's decreasing here and it's negative. If we find the point where those two change from positive to negative, we find our zero. We can find the intersection. That can tell us the intervals of where it's increasing and the interval where it's decreasing. So knowing that, let's go and take the derivative of this and set it equal to 0. All right, let's see. So 5 times 4/5 is just 4, x to the 4th. 4 times 7/2, well, that 4 over 2 turns into a 2, so that becomes 14 x cubed. Am I right about that? Yes. Okay. Minus 30x squared, and then plus 50 goes to 0. So I do not want to set that equal to 0 and have to solve that yet. I want to tidy it up a bit. What can we pull out of here? We can pull out a 2x squared. And let's see what that leaves us. That leaves us 2x squared here. And that leaves us 7 plus 7x. And then minus 15. Okay, so this is going to be equal to 0. We'll set the next one equal to 0. So that's going to be 2x squared. How do we factor this? Well, it's one of these where we have instead of an x and an x, we have a 2x and an x. So let's see, I'm looking for two things that multiply to 15. That could conveniently get us to 7. We got 5 and 3 are the most obvious. So I could put the 5 here and the 3 here. That would get me to 6x and then to 11x. Let's try putting the 5 here and the 3 here. That gets me to 10. And then if I go down 3, that will get me to 7x. All right, so now you can see where we are. We are at a point where we want to say, what values of x make this go to 0? Well, if x is 0, that means you would get 5 here, you'd get negative 3 here, but then you'd get a 0 here, which would make it all go to 0. So we know that x equals 0 is one of the zeros. How about in this little guy? Well, what x would make this go to 0? Because it's going to be multiplied through everything, so it'll make everything else go to 0 too. So we can treat each of these individually. Well, we want, if this were 3 minus 3, so what we can do is we just come out here and we say 2x minus 3 equals 0. 2x equals 3. X equals 3/2. And indeed, if you plug 3/2 in there, the 2's cancel and you get 3 minus 3. So x equals 3/2, and then x equals negative 5. These are where the slope and in other words, y prime is 0. So these indicate on a graph. So let's put 0 here. 3/2 is 1.5, so here's 1. Or no, let's make this 1, and here's 1.5. So 3/2. Then we have -5. 1, 2, 3, 4, 5, -5. We know that there's 0 here, here, and here. How do we find if they're increasing or decreasing on these other intervals? And for that matter, how do we know there aren't more zeros? Well, let's answer that first. You know there aren't more zeros because these were the only things that made this function go to 0. There aren't going to be more than that in a function as clear as this. So now let's get to the other question. How do we find out where it's increasing or decreasing? Well, we know that this is the equation of the slope. So why don't we just choose any number in this interval, plug it in, and see if it's positive or negative. That will tell us that the slope is positive or negative. Let's see. How about -1? That seems kind of easy. So if we have at x equals, sorry I was off the screen, at x equals -1, the slope y prime equals 4x to the 4th, so that would be 4, plus 14x cubed. X cubed with -1 is going to be -14, so -14, and then minus 30x squared. Well, that's going to stay negative. Okay, so we know that this right here is decreasing. How about this little guy? Well, let's just plug in 1, because he's in the interval from 0 to 3/2. We plug in 1. Y prime equals, and we get 4 plus 14 minus 30. 4 plus 14 minus 30. That is still negative. So that's negative, that's negative. And then what about at anything greater than 3/2? Well, let's go to 2. At x equals 2. We get y prime equals 4 times 2 to the 4th. Oh man, what is 2 to the 4th? Well, that's 16. 4 times 16 is, that's 32 times, 64. Okay, so that's 64 plus 14 times 8. We know that's a, let's just be rough about it. And then minus 30 times 4. What is, okay, I guess I have to be exact, don't I? 14 times 8. I'm going to pull up my calculator. That is book due. Great. 14 times 8 is 112. So instead of doing my little rough estimate, and then minus 30 times 4, which is 120. Okay, clearly we can see that 64 plus 112 is going to make this positive. All right, what does that mean for our graph? We've got a negative in this area that we found here, and then right here we found that this was positive. Well, if I were to sketch out, this is my slope, where it's positive and negative. If I were to sketch out the original function with -5 there, 0 there, and 1.5 here, I might just find that the slope was negative. And then maybe it did something funny here, but it was still negative. And then here, it became positive. That's what this tells you. And so determine where this function is increasing or decreasing. Well, how do we answer that? We say it is decreasing and then, oh, wait, I'm just realizing now, We left out one little part. We left out on this side of this number. So let's plug in -6 and see what happens. So at x equals -6, you guys are treated to my stream of conscious teaching. Y prime equals, all right, let's see what happens when we plug in -6 to this. So y prime equals, man, what is, okay, 6 to the 4th is 2,376, and then times 4 equals 9,504, plus 14 times x cubed. So that will be a negative number because we have an x cubed. So 14 times 6 times 6 times 6, 3,024. So that'll be minus 3,024. I'm writing this down here. And then minus 30x squared. So let's see what that is. Minus 30 times 6 times 6. 1,080. Okay, so minus 1,080. Well, let's do a quick check. We can tell that 9,000 is going to be bigger than these two, so it stays positive. So that means down here, it's positive. So what that tells us about our graph is that we know that from here, it went from positive slope to negative slope. And here something happened, but it's still negative. And then here, it goes positive again. So we could say it's decreasing on the interval of -5 rather, to 3/2, and increasing from, well, where does it start? Probably -infinity. -infinity to -5 and 3/2 to positive infinity. And that's how you tell where something is increasing or decreasing. And this leads us right into our next section, which is about these critical points. Critical points are these points that we found here where we set it equal to 0. Let's talk about these. X equals c is a critical point of a function if the function derivative of it at c is 0, or if f prime of c doesn't exist. Let's see what that means. Determine all critical points for this function. Okay, so let's see. F prime of x is equal to 30x to the 4th. Then we have 4 times 33 is 132. X cubed minus 90x squared. All right, let's see what happens here. Let's take some stuff out. We can factor out, looks like the biggest thing we can factor out is a 6. 6x squared equals 5, or not equals, sorry, times 5x squared plus 22x, because 6 times 22 is 132, minus 15. What do we do now? We're looking for zeros, right? We want to find where this equals 0. Those are going to be our critical points. So let's see. 0 equals 6x squared. Well, we know since this is multiplied times that, there's already going to be in our answer x equals 0, because that's a multiple. All right, now let's figure out how to factor this guy. I'm guessing we'll have a 5x and an x. And then we've got, let's see, we want to get probably 5 and 3. If we do 5 out here, that's going to give us 25, which is pretty close to that. And then we say minus 3x for the inner, and that brings us down to 22. And voila. So how do we solve for the x's? We know that x is 0. Let's set this equal to 0. 5x minus 3 equals 0. So 5x equals 3. X equals 3/5. And then x equals negative 5. So x equals 3/5, and x equals, yet again, negative 5. Those are our critical points. What do we say those points are? Well, they might be the points where, on the graph, it's changing slope. Maybe it changes 0, and then again at 3/5. Is it always going to be the points where it changes slope? We'll see. We'll see about that. But for now, that's like a casual definition that you can remember. Okay, determine all critical points for this. G of t equals the cubed root of t squared times 2t minus 1. Let's figure out the derivative of this. First, I want to rewrite it. Equals t to the 2/3 cube root times 2t minus 1. Let's see, that's going to be our f, and that's going to be our g. F prime is 2/3 t to the negative 1/3 times 2t minus 1. And then it'll be plus t to the 2/3 times the derivative of that, which is just 2. Let's see here. If we set this is equal to g prime of t. So if we set this equal to 0, what happens? Well, let's see if we can combine stuff. We set it equal to 0. Okay, 2 over 3, and that's 2 over, no, I'll just leave it like that. Sorry, 2 over 3, t to the negative 1/3 times 2t minus 1 plus 2t to the 2/3. Let's bring that plus over here. Minus 2t to the 2/3. Let's see what we can do with this. We've got minus 1 is a multiple. So if that became 0, now I see what to do. Okay, let's back up. A lot of times in calculus, you're kind of finding your way through a dark forest. And here's how I found my way through. I looked through it and I said, okay, this is kind of complicated. I want to find where all this goes to 0, which is easiest when it's one term, when everything's multiplied together, as we had in this example and the examples before. So I'm going to try to combine all this into one term. So let's see what we have here. We have 2 times 2t minus 1 over t to the 1/3. And then plus 2t to the 2/3. Well, how do we get this into one term? We have to find a common denominator, which is t to the 1/3 over t to the 1/3. Let's see what happens there. Oh, I forgot my 3 down here. I apologize. So that's going to be times 3t to the 1/3 and 3t to the 1/3 to get a common denominator. So up top, that's going to give us 6 for this little guy. That will give us 6t to the 2/3 plus 1/3 is just 6t over 3t to the 1/3. Okay, so now we have this. This is 4t minus 2. So let's see, that's our denominator. We have plus 4t minus 2. I just switched the order of these two guys. And that's 10t minus 2. So our answer is 10t minus 2 over 3t to the 1/3. And that is equal to our g prime of t. Now, when we set that equal to 0, what do we get? Well, we know if the numerator equals 0, the whole thing equals 0, so let's figure that out. 10t minus 2 equals 0. That's 10t equals 2. Divide by 10, divide by 10, and we get t equals 1/5. All right, so that's 1 point. T equals 1/5. Remember what we said here. C is a critical point if f prime of c equals 0, which we just found as 0, or if f prime of c doesn't exist. When does something not exist? When you have, typically, division by 0. So we can see here, if we plug in t equals 0, we'll get division by 0, and that is a critical point. That was a fun one. It had a nice little challenge. You figured out you had to combine this into one term to make it easy to solve. So now, let me get a drink of water. Goodness. We are going to find the critical points for r equals w squared plus 1 over w squared minus w minus 6. So let's see. We need to find r prime of w, don't we? I would suppose that we're going to have to take the quotient rule. And my mantra is, Kyle, put the denominator up top and put a minus sign. W squared minus w minus 6. And then we have times the derivative of that, which is 2w. With our minus sign, we then have w squared plus 1 times the derivative of the bottom, which is 2w minus 1, all over the denominator squared. Let's see what we get up here. If we multiply through, we get 2w cubed, that's that and that. And now we have minus 2w squared minus 12w. Now I got to be careful here. This is a minus sign in front of everything. So we're going to have minus 2w cubed. This one is negative w squared, so that'll be minus negative w squared, which is plus w squared. And then plus 2w, which will be minus 2w. Minus 1 is plus 1. Woo! W squared minus w minus 6 squared. All right, we're getting somewhere now. Let's see what cancels out. This is my favorite part. This goes away with that. Let's see what our squareds give us. Plus and then minus 2, so that'll be minus 1, so that'll be negative w squared. Okay. And then minus 12w minus 2w is negative 14w. And then plus 1 up top. And down on the bottom we've got this. I want to draw your attention to this. Can we factor that? Sure we can. That's just, what is that? W minus 3, W plus 2, right? W minus 3, W plus 2. But then the whole thing is squared, right? Because it's in the denominator of the quotient rule. Right away, we can see 2 points that are going to make this not exist. And those are going to be, I'll write them down here, W equals 3, W equals negative 2. Okay, so those are 2 critical points. How do we find up top? Well, I'm going to go ahead and spoil the surprise. There's no way to factor that except using the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. How do I know that still? It's just amazing. It just flows out of me. So this is going to be equal to negative b, which is going to be positive 14, plus or minus the square root of 14 squared, which I have no interest in doing other than on a calculator. 14 times 14, 196. Maybe I should know that eventually. Minus 4ac. Okay, so that's minus 4 times negative 1 is plus 4, and then plus 4. Ooh, that's 200. And then down here, 2a is negative 2, because you have your a is negative 1. Titillating. Okay, so 14 over negative 2. I'm just splitting up that bottom fraction, and we're going to have square root of 200 over negative 2. Well, let's see what happens here. 14 over negative 2 is negative 7. Plus or minus, how do we split up square root of 200? Well, let's see, that's just square root of 100 times square root of 2, and that's over negative 2, which means that is negative 7 plus or minus. Now that's 10 over negative 2, right? So that's just negative 5 square root of 2. So what we can say here is, because it's plus or minus, we can just say plus or minus 5 square root of 2, because it's just switched. It would be plus negative 5 square root of 2 or minus negative 5 square root of 2. Then we have 7 plus 5 square root of 2, 7 minus 5 square root of 2. Even when things get ugly, it's perfectly solvable, typically. Good. Let's do it for this one. Find critical points for h of t equals that. Well, this one shouldn't be too bad. H prime of t is equal to, we've got 10 out front, and we got our product rule. Derivative of f is just 1, then we got e to the 3 minus t squared. Oh, I shouldn't have drawn that bracket. I feel like I'm getting sloppy. Sorry, everybody. Plus, then just t times the square root, not the square root, the derivative of this, which is negative 2t, and then just times that itself. And then, let's see. Sorry, I'm just checking to see if the video is still going. Okay. You can tell my brain is slowing down. It's my second video today. Woo! Push through it. Push through it. We'll get 10 times e to the 3 minus t squared minus 2t squared e to the 3 minus t squared. So, how on earth do we solve this one? Well, we set it equal to 0. So we can divide out the 10, that goes away. And then we can say 0 equals 3 e to the 3 minus t squared. Is there any way that this can ever go to 0? No. Minus 2 t squared e to the 3 minus t squared. What about that? Let's see. Maybe there's a way we could write this that's a little more convenient, don't you think? Maybe if we brought out an e 3 minus t squared out front, and then we had 1 minus 2t squared. Now that might help us out. Because this we know cannot go to 0. E to the 0th power is 1. There's nothing you can do to make that go to 0. What about this? 1 minus 2t squared equals 0. 1 minus 2t squared equals 0. 1 equals 2t squared. That would give you t squared equals 1 over 2. And the square root would be 1 over square root of 2. And I guess that could be plus or minus. So we've found that our critical points here are t equals plus or minus 1 over the square root of 2. There you go. So it's just a matter of rearranging to try to find a nice way of finding your zeros. What about, this is the last one in this little section, f of x equals that. Well, let's see what we get. F prime of x equals, this is our f, this is our g, so we have 2x times the natural log of 3x, and then plus 6 goes to 0. But this is our second part of our product rule, is x squared over 3x times 3. So those go away. And in fact, so does the x, and it's just x. Let's tidy that up. 2x ln 3x plus x. Now if we set this equal to 0, what can we do to make this a little easier for us to solve? First off, let's bring out an x. Now we have 2 ln of 3x plus 1. So right now we know that x equals 0 is a critical point. What is the natural log of 0? What does that mean? If you have natural log, that's saying the log base e is 0. Well, it's saying e to the what power is 0? Well, it doesn't exist. So what we have there is we can't really get that. We can't get this to be 0. But let's see if we can get it to make this whole thing 0. 2 natural log of 3x plus 1 equals 0. 2 natural log of 3x equals negative 1. Divide through by 2. ln of 3x equals negative 1/2. How would you solve that? Well, let's see. You could take e to both sides. Do you remember this? Exponentiating. This brings this down. 3x equals e to the negative 1/2. That means that x equals e to the negative 1/2 over 3. And you can also write that as 1 over 3 square root of e. So that was fun, he said ironically. Okay, obviously what we've kind of been doing here is we've been finding our maxima and minima. You can find if a slope is 0, that means there's a few things happening. There's a this happening, or a that happening, or maybe even something weird where it's like leveling out for a second. So let's talk about maxima and minima. You'll love this. Absolute versus relative. Well, an absolute or global maximum at x equals c occurs if f of x is less than that point at every x in the domain. Does that make sense? You're basically saying if the function goes like this, that's an absolute maximum because it never gets higher than that. Absolute minimum is the same thing. If f of x is greater than or equal to f of c at every x in the domain. Relative maxima is a little more loosely defined, but there's one little caveat. So a relative maximum at x equals c occurs if f of x is less than or equal to f of c on some interval. Let's just call it a to b. Okay, and then relative minimum at x equals c if f of x is greater than f of c. If the function around it is all greater than this point, then that makes it the minimum on some interval a, b. Now, one thing we need to note is that relative maxima and minima, you have to look on both sides of this thing. So it cannot be a one-sided little function. Like if it goes and it ends right there, that can be an absolute minimum, but it cannot be a relative minimum because it would have to continue on the other side. Does that make sense? For instance, what do we have at each of these points? Well, what do we have? Let's go to the easy ones first. What about D? Well, that looks like it's definitely, we choose some interval around it. We say, okay, that's definitely a relative minimum, or relative maximum, sorry. And look at it, it's absolutely the absolute max as well. What about C? It's a relative minimum. Is it the absolute minimum? Looks like that point's lower. And then let's go down to this point. This we're calling the absolute maximum, or absolute minimum, sorry. Why is it the absolute? Because the absolute does not have to be two-sided. It can be a one-sided value. This is a one-sided value. It doesn't continue over here. That's the absolute minimum. What about B? Well, it's definitely a relative maximum. Is it the absolute maximum? No, that guy is. He won. What about A? Is it the absolute minimum? No. Is it a relative minimum? No. Because it's one-sided. So that's nothing. Onward and upward. Okay, these we're going to go through super fast. Find the relative and absolute extrema for y equals x squared on -1 to 2. Okay, x squared, let's chart it from -1 to 2. At -1, it's 1. At 0, it's 0. At 1, it's 1. At 2, it's 4. Great. Relative and absolute extrema. Well, let's see. What are some extrema? We've got this. we got this, and we got this. What is this one? Is it a relative maximum? No, because it's one-sided. Is it the absolute max? No, because that's higher. That's nothing. What about this guy? That's the relative and absolute minimum. And what about that guy? Well, he's the absolute max. Okay, how do we move into this, where we do it from -2 to 2? Well, we go -2 up 4. That's there. That's there. That's there. That's there. And that's there. It's just the graph of x squared. So now we got a nice little parabola. So these are our points of interest, because they're like the ones that are up the highest and the lowest. This right here is an absolute and a relative minimum, right? Because there's nothing lower than it, and it has two sides. What about these? There is no absolute max because they're both equal. And they're not relative maxes either, so we're done. All we have right here is an absolute and relative minimum. What about just y equals x squared? Well, that's something that goes like this. It goes up forever and ever in both directions. Do we have any absolute or relative maximum? No. It keeps going on and on. What about here? All we have is a relative and absolute min. So let's see here. F of x equals x cubed. This is going to be an interesting one. On -2 to 2. So I'm going to graph this out. Let's do 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. I'm going to blow up this axis a little bit. 1, 2, 1, 2. All right. At -2, it is -8. At -1, it is -1. At 0, it's 0. And then we have the mirror on this side, except it's positive. 1 cubed and 2 cubed is 8. I didn't quite draw that right. It should level out there. So, do we have an absolute min? Yes, we do. We have it right here. Absolute minimum. And this correspondingly is the absolute max. Any relative mins or maxes there? No? That's all we have. Next one. F of x equals cosine of x. Well, let's think about the unit circle. At 0, cosine is 1. What about at pi over 2? Cosine 0. What about over at pi? It's -1. Down here, it's back to 0. And then at 2 pi, it's back to 1. So what we're getting here is this sinusoidal, cosinusoidal wave. And it's going to go this way. Okay. So, do we have any relative extrema? Let's write it out properly. Relative minimum at x equals, well, where do we have the relative minimum? We have them at pi, -pi, this over here is -3 pi, this over here is 3 pi. We have them at pi, 3 pi, it would be at 5 pi, because it's just going by 2's, right? And we can say on to infinity. And then also at negative pi, negative 3 pi, and negative 5 pi, on to infinity. We have relative maxima at x equals, and where are we here? 0, 2 pi, okay. At 0, 2 pi, 4 pi, onward to infinity. And then relative maxima also in the negative direction, negative 2 pi, negative 4 pi, onward to infinity. Are there any absolute maxes or mins? No, because it's going to be repeating infinitely, and it's never going to be higher or lower at any point. And our last page, find the absolute min and max and the relative min and max. Okay, we can do this real quick, right? We can spot our absolute minimum here. Absolute min. Is it a relative min? No, because it doesn't continue right away. It's discontinuous. How about that? That's our absolute max. We've got a relative min. We got a relative max. Got another relative max. Got another relative max. And then over here, that's nothing, because it's not an absolute, and it's definitely not a relative. Okay, so this is what I'm going to leave you with. Fermat's theorem. Fermat, I assume. I don't know if he's French. If f of x has a relative extrema at x equals c, and f prime of c exists, then x equals c is a critical point of f of x. F prime of c equals 0. So this seems really obvious. If it has a relative extrema at x equals c, say like right here, and it exists, which it does, then x equals c is a critical point of f of x. Well, duh, right? That's where the slope goes from increasing to decreasing. That's a critical point. That's f prime of c equals 0 there. But be careful. A relative extrema is a critical point. This is a relative extrema. It is a critical point. But a critical point is not necessarily a relative extrema. Do you remember earlier when we did an example and we were trying to find where something was increasing or decreasing? Let me see if I can just find it real quick, because it would be very rewarding to be able to show you. Here, it was back here. It was back when we first got into this. We were talking about, we found it was negative, then we found a critical point, but we still found it was negative here. Well, let's see. That's because it went like this. It had this point where it leveled out. But it was not a relative extrema, was it? Because it was going from negative to negative. Same thing here. If we have x cubed, we know that x cubed looks like this. All right? And then x prime of cube, I'm losing it. F prime of x is 3x squared. Where's the critical point? Well, it's just at x equals 0. But x equals 0 on this does not mean that it is a relative extrema. So you have to check. You have to check on that little number line. You'd say, okay, well, if I plug in negative 1, here's x equals 0. If I plug in negative 1, that would give me, well, that would give me positive 3. If I plug in positive 1, that would also give me positive 3. So I know that this is a critical point, but not necessarily a relative extrema. All right, that's it. Good job, and homework is in the comments section. Have a wonderful day.